For years, James Webb has felt like the final word in space telescopes. The bigger mirror, the deeper vision, images from the actual dawn of the universe, it gave humanity the sense that we'd finally built the ultimate eye in space. But right now, NASA is preparing to launch something that changes the entire equation in a completely different direction. Not by looking deeper into one tiny patch of sky, but by moving so wide and so fast that it can measure the actual shape of the universe itself. As of this month, NASA is targeting August 30th, 2026 for the launch of the Nancy Grace Roman Space Telescope, a date that's already been moved up 8 months ahead of its original schedule, and the telescope itself arrived at Kennedy Space Center in Florida on June 21st, currently undergoing the final rounds of pre-launch testing. This new telescope isn't here to replace Webb. It's here to expose everything Webb was never built to chase: the invisible. Mass holding galaxies together, the force pushing the universe apart, and the roughly 95% of physical reality we still genuinely can't explain. Once it launches, astronomy may stop asking primarily what one individual galaxy looks like, and start asking what billions of them are actually doing simultaneously. On paper, this doesn't look like the obvious successor to James Webb. Roman's mirror is 2.4 meters wide, the same class as Hubble's, and considerably smaller than Webb's 6.5 meter mirror. If you judge telescopes purely by mirror size, you might assume this represents a step backward. That's exactly the trap, though, because Roman's real power was never designed around depth alone. It's designed around scale. According to NASA's own mission specifications, Roman carries a field of view at least 100 times larger than Hubble's, and by some measurements, up to 200 times larger in infrared, meaning a single Roman image can cover an area of sky that would take Hubble or Webb dozens, sometimes over 100, separate pointings to fully photograph. One is essentially a microscope, the other is a wide-angle cosmic survey machine. Webb can show you one galaxy in almost unbelievable individual detail. Roman is built to show you what billions of galaxies are doing across space and time simultaneously, and that difference in approach matters more than most casual coverage tends to acknowledge. Here's why that specific difference matters so much scientifically. The biggest open mysteries in modern cosmology, genuinely, can't be solved one object at a time. If you want to understand dark matter, dark energy, and the large-scale structure of the universe, you need real statistical power. You need enormous samples, not just individually stunning images. Roman was engineered specifically for that job. It's not trying to outperform Webb at Webb's own specialty. It's doing something Webb was never designed to do in the first place. Here's the actual reason this mission matters as much as it does. Everything humanity has ever directly touched, seen, built, or scientifically studied, all of ordinary matter combined, accounts for only around 5% of the total universe. The remaining roughly 95% is dark matter and dark energy, invisible components that dominate physical reality while remaining among the largest, genuinely unsolved problems in modern physics. Dark matter reveals itself indirectly because galaxies rotate too fast to be held together by their visible matter alone, the stars at their outer edges should, by conventional physics, fly apart entirely, and yet they don't. Something unseen is providing the additional gravitational pull holding them together. Dark energy is stranger still. It appears to be actively driving the accelerating expansion of the universe itself, pushing space apart faster and faster as cosmic time progresses. We know both of these phenomena are genuinely real, in the specific sense that their gravitational and expansion effects are directly measurable. But what either one actually consists of at a fundamental level remains deeply uncertain even now. That's exactly where Roman becomes genuinely consequential, in the best possible scientific sense. It was engineered specifically to measure those invisible forces directly through their measurable effects on light and large-scale cosmic structure, rather than simply inferring their existence loosely from a handful of individual observations. Roman isn't primarily a pretty picture telescope, even though its images will likely be genuinely stunning. It's a machine specifically built to map what we fundamentally cannot see, by carefully tracking how that invisible mass and energy distort everything else around it. Before we get into exactly how Roman plans to actually measure something as fundamentally invisible as dark matter and why its specific technique, called gravitational lensing, only becomes genuinely powerful at a scale that no previous survey has ever attempted, I want your take. Given that Roman launches in just a matter of weeks from right now, does the idea of essentially mapping 95% of the universe that's currently invisible to us feel more exciting to you than another set of individually detailed images from Webb? Drop your answer below and subscribe now, because section 2 is where we get into exactly how Roman plans to pull this off. Roman's greatest scientific weapon is a phenomenon called gravitational lensing, and understanding how it actually works is genuinely worth the effort, because it's the entire foundation this mission's dark matter mapping depends on. Einstein's general relativity tells us that mass bends space-time itself, and light traveling through that bent space-time follows the resulting curvature. That means even though dark matter itself is genuinely invisible, its gravity still measurably warps the light of galaxies sitting behind it from our vantage point on Earth. Those background galaxies end up appearing slightly stretched, subtly distorted, or correlated in shape with their neighbors in ways they simply shouldn't be, if no hidden mass were actually present between us and them. Here's the part that makes Roman's specific approach genuinely different from previous dark matter surveys. If you measure this lensing effect using a small sample of galaxies, you get suggestive hints, interesting but statistically weak. If you measure it across an enormous sample, the underlying signal stops being subtle and starts becoming genuinely overwhelming, strong enough to build an actual detailed map rather than just infer a rough outline. According to NASA's own mission planning, Roman is expected to observe roughly 1 billion galaxies over the course of its primary mission, with its core cosmology surveys specifically designed to gather weak lensing data across a substantial fraction of that total sample. That's the real leap here. Previous major lensing surveys have generally worked with samples in the tens of millions of galaxies. Roman moves into a regime that's genuinely an order of magnitude, or more beyond that, producing what should become the first truly enormous three-dimensional maps of dark matter distribution across cosmological volumes, rather than the more limited two-dimensional projections earlier surveys were largely confined to. While building that dark matter map, Roman will simultaneously measure the expansion history of the universe across roughly the past 10 billion years, using a combination of distant supernovae as standardized cosmic mile markers and large-scale galaxy clustering patterns as an independent crosscheck. That means Roman isn't only mapping where dark matter physically sits, it's simultaneously testing whether dark energy behaves consistently, the way Einstein's original cosmological constant predicted, or whether its behavior shifts in ways that would point towards something considerably more exotic, happening in fundamental physics. In other words, this single mission may end up telling us whether the universe's accelerating expansion is a relatively simple, well-understood phenomenon, or whether it's actually a signpost pointing toward entirely new physics still waiting to be discovered. As significant as that dark universe mission is on its own, it isn't the only thing Roman is built to accomplish. At the same time it's conducting its cosmology surveys, the telescope will also monitor roughly 100 million stars concentrated in the galactic bulge, the dense central region of the Milky Way, specifically watching for microlensing events, brief, precisely measurable brightenings that occur when a foreground object's gravity happens to bend and momentarily magnify the light of a background star. If that foreground object happens to have a planet orbiting it, that planet leaves its own smaller secondary signature layered on top of the main lensing event. This approach matters because microlensing is specifically sensitive to planets that transit-based surveys like Kepler and TESS routinely miss, especially colder planets orbiting farther from their host stars, the kind of worlds that more closely resemble the outer architecture of our own solar system rather than the tightly orbiting hot Jupiters that transit surveys tend to favor. According to NASA's own projections, Roman is expected to discover thousands of these previously undetectable planets over the course of its mission, giving astronomers a considerably more complete statistical picture of how common solar system-like planetary arrangements actually are across the galaxy. There's also something genuinely important that every experienced astronomer quietly understands about missions built at this scale. The most consequential discoveries are often the ones nobody specifically designed the instrument to find in the first place. Hubble did exactly that. Webb has already done it repeatedly with the impossibly early galaxies and unexpectedly massive black holes we've covered in earlier breakdowns. Roman is very likely to do the same, simply as a mathematical consequence of its own design. Once you start surveying the sky at this particular combination of scale, resolution, and repeated cadence, something genuinely unexpected becomes statistically close to guaranteed to show up. Somewhere in the data set, strange transient events, unusual lensing configurations, or entirely new categories of astronomical objects that current terminology doesn't yet have a name for. Roman's official mission is measuring the invisible universe directly. Its unofficial but genuinely expected mission is surprising the astronomers running it. Before we bring this together and look at exactly how Roman and Webb are actually designed to work together rather than compete for attention, tell me, between the dark matter and dark energy survey and the exoplanet microlensing campaign, which of these two missions do you think is more likely to produce the genuinely unexpected discovery neither NASA nor astronomers are currently anticipating? Drop your answer below and subscribe now, because Section 3 is where we look at exactly how these two telescopes are meant to function as a single combined system. One of the biggest mistakes casual coverage makes about this launch is treating Roman and Webb as rivals, competing for attention and telescope of the decade status. They're not rivals at all. They're genuinely two halves of a considerably more powerful combined system, and understanding that partnership is central to understanding why this specific launch matters as much as it does. Webb is the close-up specialist, the observatory capable of staring deep into one individual object and extracting extraordinary, almost unbelievable levels of detail from it, whether that's a single galaxy 280 million years after the Big Bang or the atmospheric chemistry of one specific exoplanet. Roman is the cosmic scout, sweeping enormous regions of sky to identify exactly where the most scientifically interesting activity is actually happening in the first place. One instrument finds the broader patterns. The other dissects individual examples of those patterns in exhaustive detail. That combination genuinely changes what's possible for the field as a whole. Roman will be capable of identifying strange gravitational lenses, unexpected supernova, unusual galaxy structures, and exoplanet microlensing signals across an enormous survey area, along with specific sky regions where dark matter appears to be shaping large-scale structure in especially revealing ways. Once those specific targets are flagged, Webb can then turn its considerably larger mirror directly toward them and study each one with the kind of individual depth and precision that Roman, with its emphasis on breadth over depth, was never actually designed to provide on its own. In other words, Roman finds where the universe is, hiding its most interesting secrets across an enormous survey area, and Webb leans in close enough afterward to actually read them in detail. That may be the single deepest reason this specific mission matters, as much as it does heading toward its August 30th launch. Roman isn't simply another telescope joining an already impressive existing fleet. It's the missing wide field engine that makes the rest of that fleet meaningfully more capable as a coordinated system. Webb has already shown us, repeatedly, what individually extraordinary objects genuinely look like up close. Roman is about to show astronomers where, how often, and at what actual scale those extraordinary phenomena are happening across the observable sky as a whole. Together, they're positioned to do something astronomy has historically struggled to accomplish simultaneously: understand both the overall forest and the individual trees within it at the same time, using the same underlying data set. There's a genuinely disruptive dimension to Roman's design that goes beyond just its individual scientific surveys, and it's worth sitting with directly. For most of the history of observational astronomy, major discoveries have typically come from carefully staring at one specific target, one particular region, one focused puzzle at a time. Roman is built for a genuinely different era, one where the sky itself becomes a data field large enough that hidden statistical patterns stop hiding, simply because no previous instrument had ever gathered enough coverage at high enough resolution with enough repeated observation to actually notice them. Roughly 1 billion galaxies for the core dark energy survey, roughly 100 million individual stars for the exoplanet microlensing campaign, a combination of cadence and total observational volume that no previous space telescope has ever brought together at anything close to this scale. When an instrument starts operating at those specific numbers, the universe stops behaving, statistically, like a collection of isolated individual objects worth studying one at a time, and starts behaving like something closer to a genuinely measurable system as a whole. That's precisely why Roman feels genuinely significant in the best possible scientific sense, rather than just as marketing. Hype ahead of launch. Moving from small, individually brilliant case studies toward genuinely planetary scale and galaxy scale census, science removes a lot of the old excuses that have historically let unresolved theoretical questions linger without a clear resolution. Either dark matter's gravitational fingerprints show up cleanly and consistently at true cosmic scale, the way current theory predicts, or something is genuinely wrong with the underlying framework. Astronomers have relied on for decades. Either dark energy behaves consistently across the roughly 10 billion years of cosmic history Roman will be measuring, or the data points toward a deeper, currently unrecognized problem in fundamental physics. Roman isn't simply broadening the total amount of astronomical data available. It's genuinely tightening the pressure on the universe itself to produce a clearer, more statistically defensible answer than has ever been possible before. Before we bring this all together in the final section, and look at what actually happens once Roman reaches its planned orbital position and begins its science operations, tell me, does the framing of Roman tightening the pressure on unresolved physics questions, rather than simply adding more pretty pictures to the archive, change how significant this specific launch feels to you? Drop your answer below and subscribe now, because the final section brings together what this partnership between Roman and Webb actually means for the years immediately ahead. So let's bring this all together, because NASA's newest telescope isn't faster than James Webb in the simple sense of being a marginally improved version of the same basic machine. It's more genuinely disruptive than that framing suggests. Webb looks deep, Roman looks wide. Webb showed us what one extraordinary individual object can actually look like under close, sustained scrutiny. Roman, once it launches on August 30th, is about to show us what billions of objects are doing simultaneously across cosmic space and time. That fundamental shift in scale is exactly why Roman may end up meaningfully changing observational cosmology more than almost any single telescope that's come before it. That's ultimately what makes this specific mission so significant right now, in the weeks before its scheduled launch. Roman was built specifically to go after the part of the universe astronomers still fundamentally don't understand, the dark matter holding galaxies, together against forces that should otherwise tear them apart, and the dark energy actively driving all of space apart at an accelerating rate. The invisible roughly 95% of physical reality that has shaped essentially everything observable in the universe, while remaining almost entirely beyond direct sight until an instrument like this existed. With a planned survey encompassing roughly 1 billion galaxies for its core cosmology mission, roughly 100 million individual stars for its exoplanet microlensing campaign, and a field of view wide enough to expose statistical patterns no previous telescope could ever have captured in a single coordinated survey, Roman isn't simply going to collect more raw astronomical data than its predecessors. It's specifically designed to force the universe itself into producing clearer, more statistically rigorous answers than have ever previously been possible. And Roman genuinely won't be working alone once it reaches its operational orbit near the Sun-Earth L2 Lagrange point, the same general region of space where Webb has already been operating since early 2022. Roman will identify the large-scale patterns, the strange transient events, the subtle gravitational distortions, and the statistically unusual outliers across its enormous survey area. Webb can then go in close and examine the most scientifically compelling of those specific targets in extraordinary, individually tailored detail, the same way it already has with objects like MOEMS-A14 and Able 2744 QS01, the impossibly early galaxy and black hole we've covered in earlier breakdowns. One telescope effectively maps the city, the other opens individual doors within it. Together, that combination represents the beginning of a genuinely new observational era, one in which astronomers may finally begin actually measuring, rather than simply theorizing loosely about, the specific forces that shape almost everything in observable existence. Here's the honest, complete picture heading into this launch. Roman's original schedule has already moved up 8 months ahead of plan, now targeting August 30th, 2026. Following the telescope's successful arrival at Kennedy Space Center on June 21st and the completion of its integration and testing phase at NASA's Goddard Space Flight Center. Its primary mission is planned to run for 5 years, though NASA's own engineers expect the onboard propellant supply to potentially support meaningfully longer operations. Beyond that initial window, once operational, it will pair Hubble-class image sharpness with a field of view at least 100 times larger, giving astronomers their first genuine opportunity to conduct true census-level astronomy, studying not just individually fascinating objects, but the actual statistical behavior of the universe as a coherent, measurable system. If this is what a single telescope, still weeks away from launch as of right now, is already expected to accomplish based on its confirmed mission design, the real question isn't really whether Roman will produce genuinely significant discoveries once it's operational. Based on everything covered here, that outcome is essentially built directly into the mission's own statistical design. The more interesting question is how many currently unresolved questions in fundamental physics, dark matter's true nature, dark energy's actual behavior across cosmic time, the real prevalence of solar system-like planetary architectures throughout the galaxy, finally get genuinely settled once an instrument exists that's actually built to survey the entire sky at this scale, rather than examine it one carefully chosen target at a time. I want to hear where you land on all of this. After walking through Roman's dark matter and dark energy mission, its exoplanet, microlensing campaign, and exactly how it's designed to work alongside Webb rather than compete with it, which part of this mission do you think will end up producing the single most consequential discovery over the next 5 years? Drop your prediction in the comments. I read every single one. And if this breakdown gave you a genuinely clear, accurately sourced picture of what's actually launching this August, instead of just the sensational headline version, do me a favor, hit subscribe, tap the notification bell, and share this with someone who hasn't heard that one of the most significant telescope launches in years is just weeks away. Thanks for watching, and I'll see you in the next one.